Hello, everybody. Dr. Mattis here. I want to talk to you today about just counting. In a chemistry class, you gotta learn how to count. Counting involves a couple different units, and it's something that students can't grasp at first, but then you just gotta think it's kind of something you're really familiar with, so don't make a big deal about it. Okay, let's not make hard out of easy. All right, but here we go. It can be hard, so we gotta take our time. Couple quick little questions. What's a dozen? Dozen is 12, right? Baker's dozen usually comes to mind, 13. Next up, you got a gross. Most kids don't know a gross is a dozen dozen. A dozen dozen, 144. So, what do we use these things? They're just counting. Dozen is 12 what? Whatever the heck you want to talk about, right? Elephants, cars, whatever. Well, if you think about it, if you're going to do atoms, atoms are really, 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 really small. In a sip of water, there are more molecules of water than you could ever count. If you go back in time to when the Australopithecines rose up on the savannah, okay, and you start counting the number of molecules of water in a drop of water, you start then because you have a really long lifespan. Okay, you go back millions and millions of years, start counting then, you still won't be done counting the molecules of water in that sip of water. So we come up with this thing called a mole. What's a mole? Not the little thing in the ground, not the little thing on your body. A mole is that many. It is a big giant number. It was derived from by Amadeo Avogadro back in the 1800s. And the thing is, nobody realized the significance of it for decades. And then they went, holy moly, this is important. It's a big number, and for big numbers like that kind of are ridiculous to write, we use scientific notation. 6.023 times 10 to the 23rd, Avogadro's number. The cool thing about the 23 and the 23, 2 times 3 is what? 6. So it's a nice way to memorize it. 6.023 times 10 to the 23rd. Don't get bent on shape. It's the same thing like a dozen. It's just a way of counting things. Alrighty? It's usually used in conversions. Alrighty? Conversions have it set up like this. You have a given unit. Already? You have this given unit. Something you're given. Like down here, I said, hey, a car is going 4.5 miles. Some number in a unit. And then you got a wanted unit, what you want to get out of it. Like how long does it take? The conversion factor is given here, but the gig is usually it's not given to you. The reason it's called a conversion factor is you're multiplying, hence the parentheses, and the things you multiply are called factors, and you're doing a conversion, so it's called a conversion factor. So don't get wigged out about, oh my gosh, what's a conversion factor? Just think, oh, it's a thing I'm multiplying by to do the conversion. No big deal. Okay, we're gonna have three main conversion factors. Okay, the gig is you can do conversions all the time. Like when you were a kid, you learned distance equals, whatever. I mean, rate equals distance divided by time. Alrighty. So let's do this one. So there you have a conversion. There's my given. Right, there's my wanted. I know I should make it blue. But to make it equal, because that double dash right there, that means it's the same on both sides. So we need to cancel out miles and introduce the unit of hour. So we put miles on the bottom, hours on top, and that way we could cancel miles and have hours equals hours. Okay? So we start off here, fill in the parentheses. Remember, you're not writing an English sentence. You don't have to start on the left and end on the right. You're sketching out an idea. Okay? So start with the given and the wanted, and then fill in the middle by letters first, then the numbers, and you do the math. Okay? How do you know you're dividing? Well, 4.5 times 1 divided by 65. Just do the math. Okay? So let's apply this to chemistry now. Okay, your first conversion factor is using molar mass. Molar mass, you basically add it up from the periodic table. If you're not familiar, like right here we got H2O. That would be 2 H's plus an O off the periodic table. H is having an atomic mass of 1.01. Oxygen is 16.00. When you add those up, you get 18.02. That number from the periodic table is the mass of 1 mole. What's a mole again? That's 6.023 times 10 to the 23rd. That many molecules would have a mass of 18 grams. That's a bigger gulp of water, but not too much. Okay? And it's a ratio. Division signs are ratios, so don't get bent out of shape on the absolute value. Like over here, don't do 1 divided by 18.2 and get a number. Just keep the ratio. Okay? Like if you had, 6 kids for 4 bikes, yeah, that's my bike, okay? The ratio would still be 4 bikes to 6 kids, okay? If we write it upside down, it doesn't really matter. So the ratios are going to be whatever way we want. depending upon our units when we set up the units, what we want to cancel. Alrighty? So first one is going to be molar mass. Okay? For example, here we got moles of nitrogen. How many moles of nitrogen? From 4.75 grams N2. So this would be our given. This is our wanted. So we can set up, just sketch out the equation, putting in your given and your wanted. We got to cancel out our grams. So the given always goes to the bottom. Wanted always goes on top. Don't write it left to right and make your life hard. I know you will. Don't do it. Just leave space for the numbers. Leave space for the numbers. It's wickedly easier. Okay? Or from the outside in. Alrighty? So then we got the periodic table. We can add up our two nitrogens. Each one is 14.01, which is where we get to 28.02. How do I know the 28.2 goes on the bottom? Because I didn't start with the numbers. I started with the letters, and the given always goes to the bottom. Second conversion, okay? Avogadro's number. Like I said up here, molecule to mole, because it's usually what we do. Over here, I'm not messing with you about writing particles. It's the number of things in a mole. Just like, you got 12 what per dozen? Whatever it is you're talking about. Well, you got 6.022 times 10 to the 23rd, whatever it is you're talking about per mole. Usually in chemistry, it's some type of particle. Electrons, molecules, atoms, whatever. That particle will be identified in the question. Like down here, I have molecules of O2. So you know you're converting molecules of O2 to moles of oxygen. Okay? So that's going to be our given. That's our wanted. So let's sketch out the equation. All right. Molecules goes to the left. That's the given. It's going to go down below so we can cancel it. Set up your equal sign. Mole goes on top. How do you know what numbers to write in there? Well, earlier, let me bump back up here. Earlier, when you did it, you had grams and moles in there. That tells you it's molar mass. It doesn't matter who's on top. Now we got molecule mole in there. That tells you it's Avogadro's number because it's particles per mole. Don't go by the mole, go by the other guy. So that's where this number comes from. It's the number of molecules in a mole, so it goes with the molecules. If molecules was on top, then the 6.022 times 10 to the 23rd would be on top. Okay? So basically just do the math. Molecules times 1 divided by that, or just 4.5 times 10 to the 24th divided by 6.2 times 10 to the 23rd. If you get this number when you crank it, and I totally advise you to do it, if you get 7.47 times 10 to the 40-something, 45th or 46th or something like that, if you get something big, then your order of operations is wrong. You're entering it into the calculator incorrectly. Okay? You have to put, if you're not using the exponential expression button, then this has to be in parentheses so that you get proper scientific notation. Our last conversion is mole to mole. It's by far the easiest conversion, and it's the one that's most missed because I think it's just too easy. Okay? Mole to mole is the time that you're going to convert one chemical formula to a different chemical formula. In the example I got here, I give you the equation. How many moles of water produced from moles of phosphine, the pH 3? So we're going from pH 3 to water. You may not know exactly how to do it, but I don't understand. Well, write down your given, write down your wanted. Put the given to the bottom, wanted on top. Now inside the parentheses, we don't see grams per mole. We don't see some particle like molecules and moles in there. We see moles of one thing, moles of something else. We need a relationship between moles of one thing and moles of something else. That is here. Okay? How do you know that these are moles? Because they're a count. If the reaction just happens one time, you need 4 of them and 8 oxygens. But if it's happening a whole mess of times in your reaction vessel, like a beaker or something like that, you got a whole lot more than 4 and 8. It's just the ratio is 4 to 8. That ratio can have units of moles. So for phosphine, it's a 4. So we're going to call that 4. For water, it's 6. So we just write those numbers in. Okay? And since those numbers are whole numbers and they're really easy to get, you don't have to memorize something, you don't have to calculate something. Students kind of put that on the back burner and it's really easy to miss. It's like, as a teacher, it's the one I expect students to miss on the test, and it is the one most missed. Lots of times people want to put molar masses in here or something like that. You don't have grams and moles, you just have mole to mole. This is the time you get 2 different chemical formulas. It's the only time you'll get 2 different chemical formulas. Alrighty, so you got 3 conversions. One use periodic table to calculate, one you memorize Avogadro's number, and the other you just go to the groovy little chemical equation and grab the coefficients. Alrighty then, have a great day. Learn it, like it, love it. I will definitely talk to you later. Take care.